Good morning. Today we are going to start Unit 2, Structure of Atom. And in this video you are going to study about wave nature of electromagnetic radiations. Structure of atom. We know that the first scientist to study about the theory of an atom is John Dalton. And we have seen the postulates of Dalton's atomic theory. And it is also found that an atom consists of 3 subatomic particles. And the subatomic particles present in an atom are electrons, protons and neutrons. Electrons, protons and neutrons. And electrons was discovered by J.J. Thomson. Protons was discovered by Rutherford. And neutrons was discovered by James Chadwick. So these are the 3 subatomic particles in an atom. And you know that you have learned in lower classes that electrons are negatively charged, protons are positively charged and neutrons are neutral. Now I have written a table here and I have written the name of 3 subatomic particles in the first column: electron, proton, neutron. And the symbol of electron is E, proton P and neutron N. Now the charge is given in coulomb, C-O-U-L-O-M-B, coulomb. And the charge of an electron is minus 1.6022 into 10 raised to minus 19 coulombs. Now the charge of proton is plus 1.6022 into 10 raised to minus 19 coulombs. And the neutron, we know neutron is neutral with no charge, so its charge is 0. Now in the last column we have the mass of these subatomic particles in kilogram. And the mass of electron is 9.10939 into 10 raised to minus 31 kilogram. Mass of proton is 1.67262 into 10 raised to minus 27 kilogram. And finally we have the mass of neutron as 1.67493 into 10 raised to minus 27 kilogram. When you check the masses of proton and neutron, they are almost nearly same, but you can see the mass of neutron is slightly greater than the mass of proton. So this is the charge and mass of the 3 subatomic particles. Now scientists tried to develop a structure for the atom, and the first scientist who gave a model for the atom is J.J. Thomson. And you have learned in lower classes Thomson's model of atom. So Thomson's model of atom, or it is also called plum pudding model. Now according to Thomson's model of atom, an atom consists of a positively charged sphere in which the electrons are embedded in it. So if you draw the structure of an atom, it consists of a positively charged sphere. Now this atom, the positive charge is uniformly distributed inside the atom, and the negative charge is embedded in it. And also we can say the number of positive and negative charges are equal in the atom, and we can say that an atom is electrically neutral. But this Thomson's model had many drawbacks. So next scientist who gave a model for the atom is Rutherford. And Rutherford, by his alpha scattering experiment, gave a model for the atom, and we call that model Rutherford's nuclear model of the atom. So the second model of atom given by Rutherford is nuclear model of atom. Now, in Rutherford's nuclear model of atom, an atom consists of a small positive charge at the center called nucleus. So, if you draw the structure of the atom consists of positive charge, and that positive charge and mass of the atom is concentrated in a small region inside the atom. We call that small region nucleus. So, this is the nucleus. And the nucleus is surrounded by electrons which move around with a very high speed in circular paths called orbit. So, you can see the electrons moving around the nucleus at very high speed, and we call this as orbit, the circular path around in which the electrons move around the nucleus is called orbit. And the last postulate given by Rutherford is that the electrons and nucleus are held together by strong electrostatic force of attraction. So, if you look in Rutherford's model of atom, you can see nucleus at the center where the positive charge as well as the mass of the atom is placed, and we can see electrons revolving around the nucleus in a circular path called orbit. So, this is Rutherford's nuclear model of atom. Now, we know that in an atom we have nucleus at the center, and in the nucleus we have the proton and neutrons, and proton is responsible for the positive charge of nucleus. Nucleus is positively charged, and the presence of proton in the nucleus is responsible for the positive charge. But the mass of atom, that is given by the number of protons and number of neutrons. Now, when you see an atom, we have nucleus at the center which consists of protons and neutrons, and electrons revolving around the nucleus. These are the electrons. Okay. Now, next we have the last model of atom, that is Bohr model of atom. Now, before we come to Bohr model of atom, we have to see some terms. Let's see those terms. The first term is atomic number. Atomic number denoted by Z. Now, atomic number means it is the number of protons in an atom or number of electrons present in neutral atom. So, you can write atomic number as atomic number is equal to atomic number Z is equal to number of protons in the nucleus of an atom, or it is also equal to the number of electrons in neutral atom. So, this is atomic number. Okay. Now, for example, you know that the atomic number of sodium, atomic number Z of sodium is equal to 11. So, you can say the number of protons present in sodium atom is 11, and number of electrons present in sodium atom is also equal to 11. Now, if it is Na plus, what do you mean by Na plus? Na plus means one electron is removed from sodium atom. So, we have Na plus will have only 10. One electron is removed. Okay, so the number of protons will remain as same, which is equal to atomic number 11, but here number of electrons will be 10 because Na plus is formed by removing one electron. Now another example, you know the atomic number of chlorine. Chlorine atomic number is equal to 17. So number of protons and number of electrons both are equal to 17. Now if it is Cl minus ion, Cl minus means one electron is gained by chlorine. So it gains one electron means the number of electrons will be equal to 18. So here number of proton will be same as atomic number, but number of electron will be equal to 18. So that is why we said atomic number is equal to number of electrons in neutral atom. If it is an ionic species, accordingly you have to remove or add electrons. Okay, so that is atomic number. Now the next term is mass number. Mass number denoted by capital A. Mass number means mass number is equal to number of protons plus number of neutrons. So A is equal to number of protons plus number of neutrons. Or we know number of protons is the same as atomic number plus number of neutrons. Or we can find number of neutrons from this if we know the mass number and atomic number. Number of neutrons is equal to mass number minus atomic number. Okay. Now we can call the neutrons and protons. We know that these neutrons and protons are present inside the nucleus. So they can be collectively called as nucleons. So nucleons means the protons and neutrons are collectively called nucleons. Now, how to represent the composition of an atom? The composition of an atom is represented as X, A, Z. Now, what is X? X means the element, the symbol of the element. And A means mass number and Z is atomic number. And we know this mass number and atomic number is written on left hand side, and mass number is written as a superscript and atomic number as a subscript. Now if you see sodium 2311, you know that this is the element sodium whose mass number is 23 and atomic number is 11. So this is how we represent or we indicate the composition of an atom. Now next let's see what are isotopes. So next term is isotope. Isotopes. Isotopes are atoms of same element with same atomic number but different mass number. Now example, we have isotopes for hydrogen atom. So the isotopes, name of isotopes of hydrogen atom is protium, deuterium and tritium. And the symbol is same, HHH. Now we know that they have same atomic number. Atomic number of hydrogen is 1 and atomic number is written as a subscript. So on left hand side. So all three isotopes have same atomic number but different mass number. Mass number of protium is 1, deuterium is 2 and tritium is 3. And out of these three isotopes, tritium is the radioactive isotope of hydrogen. And you can see they differ in the number of neutrons. The number of protons and number of electrons are the same, but number of neutrons are different. And the number of neutrons in this Number of neutrons, to find the number of neutrons, we have the expression mass number minus atomic number. So in protium, the number of neutrons is equal to 0 because it is 1 minus 1. Now number of neutrons in deuterium is 2 minus 1, so 1. And number of neutrons in tritium is 3 minus 1, which is equal to 2. And the number of protons and number of electrons will be the same in all three isotopes of hydrogen. So isotopes means atoms of same element with same atomic number but different mass number. Now the next term we have isobars. Isobar. Isobar means atoms of different element with same mass number but different atomic number. Now example for isobar is carbon. Carbon mass number 14 and atomic number 6, and nitrogen mass number 14 and atomic number 7. This is an example for isobar, carbon and nitrogen with same mass number but different atomic number. Now the next term coming is isotones. Isotones. Now isotones are atoms with same number of neutrons. Example, carbon 14, 6, nitrogen 15, 7, oxygen 16, 8. Now if you look at the number of neutrons in this, it is the same. Carbon 14, 6 means 14 minus 6, the number of neutrons will be equal to 8. 15 minus 7, 8, and 16 minus 8, 8. So this form isotones. Now last we have a term called isoelectronic species. Isoelectronic species. Isoelectronic species means atoms or ions having same number of electrons. For example, Na plus, Mg2 plus, neon, sodium plus, sodium ion Na plus means the number of electrons is equal to 10. Magnesium atomic number is 12. Here we have Mg2 plus. 2 plus means 2 electrons are lost. So the number of electrons in Mg2 plus is again 10. Neon, the atomic number of neon. Neon is a neutral molecule. Its atomic number is equal to 10. So number of electrons is also equal to 10. So this forms an isoelectronic species. So these are the terms that we have to study before we come to the Bohr model of atom. Now next we are going to discuss the developments that led to Bohr model of atom. So before we study the postulates of Bohr model of atom, we had to see what are the developments that led to the Bohr model of atom. So next we have developments that led to Bohr model. Now, there are two main developments that led to the formulation of Bohr model of atom. The first is dual character of electromagnetic radiation. Dual character of electromagnetic radiation, which means that electromagnetic radiation has wave-like properties and particle-like properties. And the second development is atomic spectra. So first we are going to study about the dual character of electromagnetic radiation. Dual character of electromagnetic radiation. And under this, I told you, dual character means electromagnetic radiation have wave-like properties and particle-like property. So first we are going to discuss what is the wave nature of electromagnetic radiation. So under dual character, first we are going to discuss wave nature of electromagnetic radiation. Now, what do you mean by an electromagnetic radiation? When an electrically charged particle moves under acceleration, alternating electrical and magnetic fields are generated and transmitted in the form of waves. It's called electromagnetic waves or electromagnetic radiation. Now, you can see on the board the electromagnetic waves. That is, when charged particles, electrically charged particles move under acceleration, we get alternating electric and magnetic field. And you can see in the diagram the electric field and the magnetic field. And this is the direction of propagation of the wave. And here you can see the electric and magnetic field have same wavelength, frequency, velocity and amplitude, but they vibrate in mutually perpendicular planes. So these are the electromagnetic waves produced. Okay, how is it produced? When an electrically charged particle moves under acceleration, we get alternating electrical and magnetic fields, and they are transmitted in the form of waves. And we call these waves as electromagnetic waves or electromagnetic radiation. Now, these waves means, what do you mean by waves? Waves are the disturbances produced that originate from some vibrating source, and they travel outwards as a continuous sequence of alternating crest and trough. So if you draw a wave, wave means we have a crest and trough. This is the crest and this is the trough. Crest means the point of maximum upward displacement of a wave is called the crest, and the point of maximum downward displacement of the wave is called trough. Now let's see some of the characteristics of these waves. The first characteristic is wavelength. These waves are characterized by wavelength. Wavelength is denoted by lambda. This is the symbol for lambda. Now what do you mean by wavelength of a wave? The distance between two adjacent crest or trough is called wavelength. That is this distance. This is one crest and this is the other one, and this distance is lambda. Or it can also be the distance between two troughs. This is also lambda. So the wavelength is the distance between two crests or between two troughs, and the unit of wavelength is usually meter or angstrom, denoted by A0, and 1 angstrom is equal to 10 raised to minus 10 meter. So wavelength is usually given in units of meter or angstrom. Now the second characteristic of a wave is frequency. So second one is frequency. Now frequency is denoted by nu. Now it is the number of waves that pass through a given point in 1 second, and its unit is second inverse or cycles per second, or it is also equal to hertz, and the symbol of hertz is Hz. This is frequency. Now the third characteristic of a wave is velocity. Velocity denoted by c. Velocity is the distance travelled by a wave in 1 second, and its unit is, it is the distance travelled in 1 second. So the unit of velocity is meter per second. Now in vacuum, all type of electromagnetic waves travel with the speed of light, and we know the speed of light is 3 into 10 raised to 8 meter per second. Now the next term that characterizes a wave is amplitude. Number 4 is amplitude. Amplitude denoted by capital A. Amplitude means it is the maximum up or down displacement of a wave. That is, when you see this wave, amplitude is this height. This is the amplitude of the wave. The maximum up or down displacement of a wave is its amplitude. And the unit of amplitude is meter. Meter. Now, the last term that characterizes a wave is wave number. Number 5. Wave number denoted by nu bar. Wave number is the reciprocal of wavelength, or it is the number of wavelengths per unit length, and it is the reciprocal of wavelength. So we can say nu bar is equal to 1 by lambda, and the unit of lambda is meter, so the unit of wave number will be equal to meter inverse. Now there is a relationship between C, nu and lambda, and the relationship is C is equal to nu lambda, where C is the velocity, nu is the frequency and lambda is the wavelength. Now you can get the expression for frequency from this. Nu is equal to C by lambda, and we know 1 by lambda is nu bar, so you can write this as C nu bar. So these are the different expressions, or expression that relates velocity, frequency and wavelength. That is, C is equal to nu lambda. Now next let us see the properties of electromagnetic waves. Properties of electromagnetic waves. The first property is that the electric and magnetic field produced by charged particles are perpendicular to each other, and both are perpendicular to the direction of propagation of wave that we already discussed. Now the second property is that unlike sound waves or water waves, electromagnetic waves do not require any medium to travel. Means it can move in vacuum. Now the third property is there are many types of electromagnetic radiations which differ from one another in frequency or wavelength, and these constitute what is called the electromagnetic spectrum. So what do you mean by an electromagnetic spectrum? Electromagnetic spectrum. Now, electromagnetic spectrum means the arrangement of electromagnetic radiation in increasing order of wavelength or decreasing order of frequency is called electromagnetic spectrum. So, in this electromagnetic spectrum, we have different electromagnetic radiations arranged in increasing order of wavelength, and we know wavelength and frequency, they are inversely proportional. So increasing order of wavelength or decreasing order of frequency, and we have these radiations in the electromagnetic spectrum. I'll write that names. Cosmic rays, I'm arranging in increasing order of wavelength. Cosmic rays less than gamma rays, less than X rays, less than UV rays less than visible, less than IR, infrared rays, less than microwaves, and less than radio waves. So these are the different radiations present in the electromagnetic spectrum in increasing order of wavelength. So increasing order of wavelength means the radio waves has, this is in increasing order. So radio wave has the highest wavelength and lowest frequency. Now cosmic rays has the lowest wavelength and highest frequency. Okay, so this is our electromagnetic spectrum, and here the radiations which are visible to us is the visible rays. Now in the visible rays we have the light, Vibgyor, and you know Vibgyor, red has the largest wavelength and violet has the smallest wavelength, and since the wavelength of red light is the longest, it has the lowest frequency. Okay, now next, limitations of electromagnetic wave theory. Now this theory could explain many properties of waves like diffraction and interference, which you need not study here. So the limitation of electromagnetic radiation is, though it could explain some of the properties of waves, some other properties like black body radiation, photoelectric effect, and line spectrum or atomic spectrum was not able to be explained by this wave nature of electromagnetic radiation. So it was found that this electromagnetic radiation has another character called particle nature of electromagnetic radiation. So these were the limitations of electromagnetic wave theory. It could not explain black body radiation, photoelectric effect, and the line spectrum. And these limitations were explained by particle nature of electromagnetic radiation. Thank you.